So now we're going to go over our practice problems for C13 NMR. And our first problem here is one that asks us, basically, here's a compound. Predict, draw what the C13 spectrum is going to look like. Now, a lot of times students will ask, why do we do problems like this? Isn't most of what we're going to do in this course, or, in practice, is to look at spectra and interpret them? The answer to that is yes. But it also becomes very important in many situations that you have an idea of what your spectrum it should look like. And that's something you can do by practicing situations like this. Now, in a problem like this, I'm not going to expect that you can get every peak in exactly the right spot. But what I'm looking for in a problem like this is that you have peaks in the right range and that you have the right number of them. So how would you start on a problem like this? Well, I would start by getting out my chart. And that could be, this one, which is posted for you on Blackboard and is the one that I would give you on an exam. Or it could be any other chart, such as one you find in the textbook. The important thing to keep in mind is just to remember that I don't expect you to memorize these ranges. Just like with IR, don't expect you to have to memorize all of these shifts. And that you would have a table like this to use. So I'm going to zoom out here so we can see both the table as well as where we're going to plot the spectrum at the same time. So some of these peaks have fairly large ranges, such as the aromatic ring, for example. We know an aromatic ring could be anywhere from about 100 to 160 ppm. So what I'd be looking for in that case is not that you have the peaks at exact numbers, just that you have the right number of peaks in that aromatic region. Now, first thing we could ask ourselves is how many peaks do we expect to see in this spectrum? And so take a moment and count up the number of different types of carbons that you'll have. Because remember, the number of different kinds of carbons that you have in a molecule is the determination for how many peaks you're going to get. So what you should have come up with is that we should have 12 peaks in this spectrum. And so what we're going to start with are these two methyl groups at the end that are attached to the alkene. We're only going to... So what I should say about the 12 peaks is right now I would expect you to come up with 12 peaks. As we learn more about stereochemistry later on in this course, you'll actually learn that these two methyl groups on this alkene are not equivalent. And so in reality, this compound will have 13 peaks. But for our purposes today, we're going to stick with 12. The difference is these two methyl groups are actually not equivalent. And they're not equivalent because of that alkene. Again, that's something that we'll get to in more depth in Chapter 10. But it is a methyl group at the end of a chain. If we look at our chart, that shows up around 8 to 30 ppm. Given this one's attached to an alkyne or an alkene, I might expect it to show up a little bit higher, but again, within that region. We then move on to these two alkene peaks. Alkenes, same region as aromatic, 100 to 150. And so we'll just fill in 2 peaks for the alkene. Then we've got our aromatic ring. Our aromatic ring here is symmetric. That symmetry goes this way. And so we should see 4 peaks in our aromatic region. Again, at this point, we're not worried about where in the aromatic region you put them, just that they're somewhere within that range that makes sense for an aromatic. Next to the aromatic, we have a carbonyl. And specifically, that carbonyl is an ester. Esters show up 155 to 185. So I'm going to put that carbonyl peak right in that ester range. And hopefully I'll make it look like only 1 peak. Next to that, we have a carbon that's attached to an oxygen. Those show up between 40 and 80 ppm. We have the 2 alkyne carbons, which we can see on our chart right below the carbon-oxygen, between 65 and 90. And finally, we have another methyl that's at the end of the chain, and we know those are fairly low in chemical shift as well. So again, the key here is that we have the right number of peaks and that we have them in the right regions. I'm not worried about whether you have a peak at 25 versus 20 or how tall the peaks are. Those are lesser concerns at this point. It's just, are the peaks in the right region, and do we have the right number? All right, our next 2 questions are asking to go the other direction. So here's a spectrum, here's a structure, assign the peaks to the structure. So when I look at this molecule, the first thing I see is a very high chemical shift peak, down around 170. And we know that up that high, the only thing we're likely to have is a carbonyl. But a lot of times, if I want to not be ambiguous, what I'm going to do is just assign a number to each different carbon in this molecule. And then that way, I can just put that number next to the peak. That's also a good way to do it when you're working in the lab. Assign each carbon or hydrogen in the molecule a number, and then you can just put the number next to the peak. Now you'll notice right around 130 ppm we have 2 peaks. And they're almost the same chemical shift, so they're going to be hard to distinguish. So we know that these are 130, that's in both the alkene and the aromatic region. We don't have any aromatic groups in this molecule, so we know those are going to be the alkene. Do we know which one's which? No, and that's actually a question that's going to be very difficult to answer. We wouldn't be able to answer it from just this spectrum. So we could just say that these 2 peaks are carbons 1 and 2. We now have these last 4 peaks for peaks that are in a straight chain. Probably the easiest one to identify is this one at about 65 ppm. Being so much higher in chemical shift than the other 3, we know that that's the one that has to be next to an electronegative element, such as oxygen. And then the further away we get from that oxygen, the lower the chemical shift will be. As we move on to number 3, first thing we should see in number 3 is that this ring is completely symmetric. So we only have to worry about half the carbons here. Now, what should be the easiest peak to identify is again the carbonyl. Carbonyls are really the only things that show up past about 160 ppm. So we know that this is our carbonyl carbon. The next peak that we're likely to identify is the one next to the oxygen. Again, next to the oxygen, if you go back up to your chart, are generally 40 to 80 ppm, but 60, right in the middle is a good place to find them. So this one around 60 is most likely to be our carbon number 5, the one that's next to the oxygen. And we can be very safe in that assumption because if you think about the other functional groups here, there's really nothing else that's going to take us to that high of a chemical shift. The next easiest peak, in my opinion, to identify is number 6. And that's another thing that I think is important to think about when you're approaching one of these problems. Start with what's easy. Some of these peaks are easy to figure out. Some of them are very difficult. Some of them are much easier. But a methyl group at the end of a chain we know are generally our lowest chemical shift peaks. Now we have just these 3, 1, 2, and 3. And the only real difference in them is how close they are to a carbonyl. Well, is a carbonyl an electron donating or an electron withdrawing group? Well, probably the most straightforward way to think about that is that in a carbonyl, we always have resonance. And that resonance puts a positive charge on carbon. And so carbonyls are, in general, electron withdrawing groups. So the closer we are to the carbonyl, the stronger we feel that effect, and should be higher chemical shift. And that's very similar to what we saw with the oxygen in the previous question. The closer we were to the oxygen, the higher the chemical shift. As we move further and further away, our chemical shift went down. All right, our last problem is starting to get into what we're going to end up with and end up doing a lot of, especially once we've learned proton NMR. Here's a chemical formula, here's a carbon spectrum, here's an IR spectrum. What compound do we have? So I often find the easiest way to start is by doing degrees of unsaturation. So 2 times the number of carbons plus 2 minus hydrogens. We don't need the rest of the formula because we only have carbon, hydrogen, and oxygen. The number of carbons is here, the number of hydrogens is here, and the number of oxygens has no impact, divided by 2. So we have 5 degrees of unsaturation. So the first thing that suggests to me is that we probably have an aromatic ring. Why? Well, this is a lot of degrees of unsaturation for such a small molecule. And so the only way we can really get that high is with an aromatic ring, which will account for 4 degrees of unsaturation. All right, what do we see in the IR that stands out to us? So the first thing that would jump out to me is over here above 3,000. I can say with absolute certainty there's no alcohol in this molecule. But in addition to that, I have this peak here. That's 1686. So that tells me I have either a carbonyl or an alkene. Now, I don't know which one yet, although in my experience, I'm going to lean towards the carbonyl here. Why? Well, this peak is very, very strong. And that's more indicative of a carbonyl than it is an alkene. But what will tell us for certain? Carbon 13 will tell us for certain. Alkene is going to show up in the same region as the aromatic ring, whereas a carbonyl is going to show up much higher. The other thing I want to draw your attention to is when we look at our carbon spectrum, note that there's two separate peaks at 128 ppm. So let's just make sure we remember that. And just so we don't forget, I'm going to write that in. So what that means is we have a total of 4 peaks in this region. And so that serves even more strongly to suggest that we have a an aromatic ring. Now, up here around 200 ppm, we have a carbon peak. And so we've confirmed that we definitely have a carbonyl in this molecule. And then down here we have what looks like it's probably, is definitely a hydrocarbon and could be a methyl group at the end of a chain. So now, to me, there's 3 possible ways to put this molecule together. And I'm going to draw all 3 of them out, and then we're going to determine which one's correct. So we could have an aromatic ring with a methyl on one side and an aldehyde on the other. Because remember, that carbonyl peak is in the range of both a ketone and an aldehyde. We could have a CH2 off the aromatic ring and an aldehyde coming off of that. Or we could have an aromatic ring with a ketone. All 3 of these are symmetric, so we could draw a line of symmetry through the aromatic ring. That would give us our 4 peaks in the aromatic region. And it has either the ketone or an aldehyde, as well as a hydrocarbon piece. But 2 of these are aldehydes, and you may recall from when we learned IR that if we have an aldehyde, not only do we get a carbonyl peak in the IR spectrum, but we get 2 peaks between 27 and 2900. And as soon as we go back up to this IR spectrum, we can see very clearly there's no aldehyde CH here. And if there's no aldehyde CH, there's probably not going to be an aldehyde in this molecule. So at that point, I can eliminate 1, and I can eliminate 2 because they're both aldehydes, and I can be almost completely certain that this is our correct answer. So going forward now, as we jump into proton NMR, we're going to start seeing a lot of problems like this, where here's a bunch of different spectra, tell me what our compound is. And that's where we're going to go from here. But before we do that, we've got to learn some proton NMR first.